Hello and welcome to MyScience Tutorials. In today's video, we are going to be talking about calculations on heat capacity and latent heat capacity. Before we begin, if you are new to MyScience Tutorials, kindly consider subscribing and pressing that notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. Now, in our previous tutorial, we did mention what heat capacity is and what latent heat capacity is, and we also saw some basic one or two examples on them. Now, in this tutorial, we want to look at a full set of questions to further understand our knowledge about heat energy. So the first example we want to look at is a metal block of mass 60 grams is heated to a temperature of 100 degrees Celsius. The block is then placed in a vessel containing 150 grams of water at 20 degrees Celsius. Now, if the final steady temperature is 25 degrees Celsius, we have to calculate the specific heat capacity of the metal, neglecting the heat capacity of the vessel, given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. So let's go ahead and look at what are the parameters that we have for this particular example. So let's write down our solution. Alright, so we have a metal block of mass, so it means the mass of the block, MB, is what? 60 grams. Okay, so if we convert that into kilogram, because the mass needed for this calculation should be in kilogram, so this will give us 0.06 kilogram. Alright, so a metal block of mass 60 is heated to a temperature of what? 100 degrees Celsius. So it means the temperature of the block is what? 100 degrees Celsius. Now the block is then placed in a vessel containing 150 grams of water. It means the mass of water is what? 150 grams. If we convert that into what? Kilogram, we get 0.15 what? Kilogram. Alright, so water at temperature 20 degrees Celsius. So it means the temperature of what? Water is what? 20 degrees Celsius. So if the final steady temperature, so it means the final temperature of the metal ball in the water within the vessel, the final steady temperature is what? 25 degrees Celsius, after the metal ball has lost some of its heat energy to the water and then the vessel. So we have to calculate the specific heat capacity of the metal, neglecting that what the heat capacity of the vessel, or we are neglecting the heat capacity of the vessel. So we have the specific heat capacity, which is what? Small c of water is what? 4,200 joules per kilogram per Kelvin. Alright, so now that we have the parameters, let's go ahead and look at how to solve this problem. Now we have a metal ball that we've heated, or we've applied heat to it, and then we transfer it into a vessel containing water. So it means, okay, what it means is what? The heat lost by the metal, by the metal is equal to what? The sum of the heat gain, that is heat gained by the vessel and the heat gained, okay, by water. So it means the heat that the metal ball has lost when it was transferred into the vessel containing the water is equal to the heat gained by that vessel and then the water within the vessel. Now the question is telling us to neglect, okay, the heat capacity of the vessel. So it means the entire heat gain by the vessel we are assuming is negligible. So in this case, this will be crossed out. So it means the heat lost by the metal is equal to what? The heat gained by the water. Now we know heat, which is Q, is what? The product of mass of, so this is the metal, so mass of what? Metal. Specific heat capacity of metal multiplied by what? The change in temperature of the metal should be equal to the heat gained by the water will also be what? The mass of water, the specific heat capacity of water, and then what? The change in temperature of water. Now we are given the mass of the metal to be what? 0.06. Then the specific heat capacity of the metal ball, that is what we have to find, so Cm. Then the change in temperature over here. Initially the metal ball was at what? 100 degrees Celsius. Okay, so we have 100 over here. Then after it has been transferred into the water, the final steady temperature is now what? 25. So the change in temperature will be what? 100 minus what? 25. This is equal to the mass of water is what? 0.15 multiplied by the specific heat capacity of water, which is what? 4,200. And we multiply that by what? The change in temperature over here is what? We can see that the temperature of water initially was 20 and then the final steady temperature is 25. So the difference has to be positive. So we subtract the 20 from the 25. So we get this. So now that we have this, we can simply move ahead and find our what? Cm. So if we multiply 0.06 by the difference of this, we are going to get what? 4.5. Okay, Cm to be equal to, if we multiply everything over here, we are going to get 3,150. So if we divide both sides by 4.5, we are going to get the specific heat capacity of the metal to be what? 700 what? Joules per kilogram per what? Per Kelvin. So this is the specific heat capacity of the metal block that was placed in the vessel containing 150 grams of water. Alright, now let's go ahead and look at another example. So example number 2, we want to look at a block of ice of mass what? 2 kg at negative 10 degrees Celsius is heated until it forms water at what? 50 degrees Celsius. We have to calculate the total heat involved in this process, given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin, and then the latent heat of fusion of ice is what? 336,000 joules per kilogram. So let's go ahead and solve this question. So we write down our solution. Now let's look at the transformations that will occur during this process. Let me use another ink for that. So let me use dark blue. Alright, so we can see that a block of mass 2 kg. Okay, so it means the mass of block is what? 2 kg. The initial temperature of the block, that is T initial of the block, is what? Negative 10 degrees Celsius. Now it's heated until it forms water at what? 50 degrees Celsius. So it means the final temperature is what? 50 degrees Celsius. Okay, so we have to calculate the heat involved in this process. Now, one thing we need to note is that what? The ice is solid, okay, and then the water that we now have at 50 degrees Celsius is liquid. So we can see that there is a change in state of matter. So we need to account for that as well. So it means, first of all, we need to convert, okay, or change ice, okay, at what? Negative 10 degrees Celsius to what? Ice at what? 0 degrees Celsius. Now that if we are able to convert or apply some heat to convert the ice at what? Negative 10 degrees Celsius to 0 degrees Celsius, we now do what? Convert the ice, okay, at what? 0 degrees Celsius to water at what? 0 degrees Celsius. Okay, so the ice will now apply a certain amount of heat to it so that it will melt into water, and we can see that we are moving from solid, which is the ice, to water, which is what? Liquid. So there's a transformation or there's a change of matter, okay, or change in state of matter from what solid to liquid. So this amount of heat or this heat needed over here is what we call the latent heat of fusion. So latent heat of what? Fusion. Okay, latent heat of fusion. Now the third one is what? We need to convert water, okay, at what? 0 degrees Celsius to water at what? 50 degrees Celsius. Okay, so which is now the final temperature of the water that we have. So this, the energies involved in these 3 steps, the sum of all of them will give us the total energy that is involved in this process. So let's take them one by one. So let's have Q1. Okay, that is the heat energy involved in changing or in converting the temperature of the ice at negative 10 degrees Celsius to 0 degrees Celsius. So the heat energy over here will be the product of what? Mass of the ice. Okay. Okay, this is ice block, so let me use I. So the mass of the ice, okay, the specific heat capacity of the ice multiplied by what? The change in temperature of the ice. So Q1 is equal to the mass of the ice is what? 2 kilograms. Then the specific heat capacity of ice, we were not given, but then from literature, the specific heat capacity of ice is what? 2100. Okay, all right. So the question will give that to you, but I forgot to write it down. So the specific heat capacity of ice is 2100. Then the change in temperature over here is, we are converting from negative 10 to 0. So 0 is definitely bigger than negative 10. So we have 0 minus what? Negative 10. So we have our Q1 to be equal to what? If we multiply 2 by this will give us what? 4200 multiplied by what? 10. And then Q1, which is the heat involved in the first process, is what? 42,000 joules. Alright, so let's find Q2. Okay, now Q2 is what? Converting the ice from 0 degrees Celsius to water at the same temperature, and that is what I'm calling what? Latent heat of fusion, because there is a change in the state of matter but then at the same temperature. So in this case, the heat involved in this process is just the mass of the ice multiplied by the latent heat of fusion of ice, and that will give us what? The heat involved in this process. So in this case, it will become Q2 is equal to the mass is still 2 multiplied by the latent heat of fusion of ice is 336,000. Okay, so it means Q2, or the heat involved in converting the ice to water at the same temperature, in this case, is what? 672,000 joules. Okay, now let's look at the final heat energy involved, so Q3. Now the final energy involved in this process, okay, we are converting from 0 to 50, so it will be what? The mass of water, specific heat capacity of water, and then change in temperature of the water. Now the mass of the water, we assume, is still the mass of the ice, provided no matter was lost during the conversion of ice to water. So we still use 2 multiplied by the specific heat capacity of water is 4,200 multiplied by the change in temperature will be what? 50 minus 0. So we have what? 8,400 multiplied by 50, and this will give us what? A total heat energy of 420,000 joules. All right, so our total energy involved, or the total heat energy involved in this process, which is Q total, is the sum of what? Q1 plus Q2 and what? Q3. So it means our Q total will be what? The sum of what? 42,000 plus 672,000 and 420,000 joules of energies. So the total will be what? 1,134,000 joules of energy. So this is the total amount of energy needed in joules to convert an ice block of what 2 kilograms at negative 10 degrees Celsius to water at 50 degrees Celsius. So let's proceed to look at another example. Now, example number 3, we have water of mass 2 kilograms at the temperature of what 30 degrees Celsius is heated by a 5.0 kilowatt coil. So we have to calculate the time taken by the water to boil, given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Alright, so let's write down our solution. So first of all, let's look at the parameters that we have. So we have water of mass, so it means the mass of water is what? 2 kilograms. So the initial temperature of water is what? 30 degrees Celsius. And it's being heated by 5 kilowatt core, so that is the power of the core. So the power is what? 5.0 kilowatt. Alright, so we have to calculate the time taken. So the time is unknown, taken by the water to boil. So we have specific heat capacity of water, CW, to be what? 4,200 joules per kilogram per Kelvin. Alright, now we have a new parameter over here. So power, okay, power is equal to what? Heat applied over what? Time taken. Okay, so our time is T, our heat is what? Q. Okay, so now that we know that the formula of power involves what? The heat applied, the ratio of the heat applied to the time taken, we need to first of all find what? Our heat applied to boil the water from what? 30 degrees Celsius to what? 100 degrees Celsius, because they say the water boils, so it means our final temperature, okay, final temperature is what? 100 degrees Celsius. Okay, so we need to find the heat involved in this process. So the heat will not be what? The mass of water multiplied by the specific heat capacity of water multiplied by the change in temperature of the water. So our heat is now what? 2 kilograms multiplied by 4,200, that is the specific heat capacity of water, multiplied by the change in temperature over here will be what? 100, because the question is saying calculate the time taken for the water to boil, and we know water boils at what? 100 degrees Celsius. So the initial temperature over here is what? 30. So if we do the multiplication, we get here 8,400 multiplied by what? 17. So our heat energy involved in the first our heat energy involved over here is what? 588,000 joules. Okay, so this is the heat energy involved in this process. So now that we have our heat energy involved, we just need to make time taking the subject over here, and then we've answered our question. So if we make from here, if we make time the subject, time taking the subject, okay, we get to realize that our time taken will be what? The ratio of the heat applied, okay, to the power of the core. Okay, so it means our time is equal to our heat, which is what? 588,000 on the power, okay, is what we have over here, 5 kilowatts. So we have 5 times 10 raised to the power 3 for the kilo. All right, so our time is equal to, the ratio of this is equal to what? 117.6 seconds. Okay, then for convenience sake, if we convert the time from seconds to minutes, we are going to get 1.96 minutes. Okay, that is, we divide this by what? 60, and then we get what? 1.96 minutes as the time taken for the 5 kilowatt core to boil the water, or to boil 2 kilograms of water at 30 degrees Celsius to 100 degrees Celsius. Alright, let's have a look at one final example. So we have an electric heater operating at a 230 volt supply. Is used to heat a metal ball of mass 600 grams. which is at an initial temperature of what, 30 degrees Celsius. So we are to the question is saying if the current passed is what, 5 amperes, we have to calculate the time it takes to heat the metal to 90 degrees Celsius, and we are given the specific heat capacity of the metal to be what, 460, so is 460 joules per kilogram per Kelvin. Sorry for that mistake. Alright, so let's write down our solution. Alright, so we have an electric heater operating at a voltage supply of what, 230. So our voltage is what, 230 volts. Okay, so it's used to heat a metal ball of mass 600 grams. So the mass of what, the metal, let me use MB as the ball, is what, 600 grams. So if we convert this to kilograms, we are going to get what, 0.6 kilograms. Okay, so the initial temperature of the ball is what, 30 degrees Celsius. Okay, so we have a current of 5 amperes passing through it. So we have to calculate the time taken, okay, to heat the metal ball to what, a final temperature of what, 90 degrees Celsius. Alright, so let's look at how we solve this question. Now the heat, okay, heat is what, our Q, okay, can be given as what, the product of what, the current, voltage, and then time. Okay, so if you apply a current at a particular voltage through water for it to heat, okay, if you want to calculate the amount of heat that you applied, you just multiply the current passing through the system with the voltage and then the time taken for the water to boil. So it means our heat energy is equal to what, IVT. But we also know that our heat, okay, in this case that we are using, is what, the product of what, mass, okay, specific heat capacity, and then change in temperature. So it means we can equate these two equations. So it means the product of voltage by current and time is equal to what, the mass, which is in this case mass of the ball, specific heat capacity of the ball, and then change in temperature of the ball. Alright, so we have our voltage, which is 230 volts, multiplied by the current is 5, okay, and then the time we don't know. The mass of the ball is what, 0.6 kilograms, multiplied by the specific heat capacity of the ball is 460, then multiplied by the change in temperature will now be 90 minus 30. Alright, so if we multiply 230 by 5, we get what, 1150 multiplied by the time to be equal to, if we multiply everything over here, we get 16,560. So we have 16560. So if we divide both sides by 1150, we get our time to be equal to what, 14.4 seconds. So it means it took 14.4 seconds, okay, for the electric heater to warm the water, which is at 30 degrees Celsius to 90 degrees Celsius, provided a voltage of 230 volts is applied, and then the current passing through the system is 5 amperes. So thank you so much for watching, and I will see you in the next video. Bye bye.